Thank you. My name is Rikizo Ikuta from Osaka University. I am an experimentalist related to the quantum internet or the quantum interconnect between the different matter systems or matter and photonic systems. And today I will introduce recent work related to the quantum manipulation of photons using the frequency degree of freedom, and brief introduction related to this field. And quantum internet is a quantum version of the current internet, and which was summarized in this paper. And for realizing the quantum internet, this is a figure of the quantum sensor networks, but by at the end nodes, the quantum sensors are included in this network system. But when we use quantum processors or quantum devices instead of the quantum sensors, this can be understood as a general network of the quantum internet, and which includes the quantum processors or sensors and memories and random number generator and the quantum switches and very many components. And especially for the key device of the photonic related to the photonic device, there are many components for realizing the quantum internet. And today, in this list, there are a lot of components related to the frequency manipulation of photons. And today, I will introduce these technologies. And quantum first of all, I will introduce the quantum frequency conversion, which converts the frequency of photons at a frequency to a different frequency while preserving the quantum information. And there are several approaches to realize the frequency conversion of photons, but most major approach to realize the frequency conversion is using the Kaitsu nonlinearity, like this figure. That is the three-way mixing processes of similar to the conventional nonlinear interaction. And in this energy diagram, the highest energy photon has a frequency of omega h, and the lower frequency is described by omega L1 and omega L2. And there are important two processes. The first one is the frequency conversion, and the second one is the photon pair generation. And we focus on the first application of this talk. And this process uses a very strong pump lasers at the lowest energy omega L2. And in this case, the Hamiltonian of this three-way mixing process can be described by this effective Hamiltonian using the beam splitter interaction between highest energy photons and the lower energy photons. So using this process, the process of the frequency conversion can be understood as the two-mode beam splitter interaction between omega h and omega L. So similar to the conventional beam splitter interaction of the spatial mode, the photons can be reflected to the different frequency from the another frequency. And okay, I will explain the detail of the quantum frequency conversion based on the Kaitsu nonlinearity. The signal photon is the omega s, and the converted light photon is omega r, and with the strong pump light omega p. And in this case, the effective Hamiltonian is the beam splitter interaction between the omega as and ar. with a coupling constant Xi. And the Xi is proportional to the complex amplitude of the pump lasers like this. So by solving this Hamiltonian using the Heisenberg picture, we can obtain the beam splitter interaction of this process between the AS and AR. And to understand this solution, I explained that I used this slide. The frequency conversion system is described by this Hamiltonian, and this is a unitary interaction between the two modes, AS and AR. And this can be understood as a transformation from AS in to AS out. But it is difficult to directly solve this unitary transformation from AS in and to AS out using the Schrödinger picture. And instead, in conventional approaches, we can use the Heisenberg picture instead of the Schrödinger picture, like using this Heisenberg equation, like previous lecture. So using this equation, we can easily solve the time evolution of the AS and AR. And then by using these equations, we obtain the input-output relation between the two different frequency modes. And from this, the transmittance of this beam splitter interaction is described by cosine, and the reflectance is described by the sine. So for the frequency conversion from AS mode to AR mode with a unit efficiency, theta equal pi is the best condition for the maximum conversion efficiency. And in experiment, what level pump power is required when the conventional PPN waveguide is used for the nonlinear optical material. One of the interesting point of this the frequency conversion is this can be regarded as a linear optical the unitary operation in spite of the while the interaction is a nonlinear optical interaction. The physics behind the linear interaction is the use of the very strong pump lights. So this three-mode interaction can be regarded as the two-mode linear two-mode beam splitter interaction. So as a result, this can be regarded as a unitary transformation between the two modes, two different frequency modes. And the frequency conversion is very commonly used in the context of the quantum internet or the interface between the matter and the photons, like this figure. The quantum systems, the matter quantum system has resonance levels in which the particular frequency can interact with the matters, and the other frequency photons never interact with the matter qubit. So, but the resonant frequency usually does not match the wavelengths for the optical fiber communication or the suitable for the high efficient quantum communication wavelengths. So, for example, I list the candidates of the quantum memories or the quantum processors, and wavelengths of the photons interact with the matter systems. For example, in our laboratory, we use the Ruby atomic system, which interact with the 780 nanometer photons or 795 nanometer photons. But these wavelengths are not compatible with the telecom wavelengths photons around 15 nanometers with minimal optical loss for the optical fiber communication. So to bridge the frequency mismatch between the these wavelengths and the telecom wavelengths, we use the quantum frequency conversion. And in our laboratory, we demonstrated the QFC experiment using this wavelength and the 637 nanometer photons for NV centers and 866 nanometer photons emitted from the calcium ion systems. And this is the conceptual figure of the quantum photonic communication emitted from the quantum matter system with the use of the quantum frequency conversion. The photon entangled with the matter qubit is frequency converted to the telecom photon, and then it is transmitted through the optical fibers. And the transmittance of the optical fibers are listed in this table. Around the 800 nanometer photons, like the photons emitted from the rubidium atoms or other major candidate matter systems. The loss coefficient of the optical fibers is about 3 dB per kilometer. So after the 10 kilometer communications, only the 0.1% efficiency remains. And on the other hand, when we use the telecom wavelength photons, the loss of the photon is very small, 0.2 dB per kilometer. So even if the photons are transmitted through 100 kilometers, 1% photon remains after the transmission. So this graph shows the transmittance versus fiber length. And this is for telecom photons, and this is for the visual wavelength photons. And so even if the QSC efficiency is not perfect, and for example, the QSC efficiency is only 0.1%, the transmittance after the QSC becomes larger when we communicate with the photons over long distance, about 10 kilometers. So in practical situations for the quantum internet over long distance, for example, the 10 kilometer or 100 kilometers, the QFC technology is one of the key components for realizing the quantum internet using the matter system that's the end node. So in the current, the state-of-the-art experiment reported from the Weinfelder group, about 60% QFC efficiency was achieved. So the transmittance line, including the QFC, becomes like around this line. So many experiments using the optical fiber systems uses the QFC in the current demonstrations. And in our group, we have achieved the first demonstration of the QFC from the visual wavelengths to the telecom wavelengths using the PPL waveguide. In the demonstration, we use the integral photon pair prepared by the spontaneous parametric down conversion. And photon at the 780 nanometer is converted to the 1522 nanometers of the telecom wavelengths using this QFC system. The Kaizen nonlinearity, the material of the Kaizen material is PPN waveguide. It is a very standard material used in the QFC experiment or other nonlinear interaction in the photonic quantum information processing. And using the pump light at 1600 nanometers, the photon is converted to this wavelength. And using the black grating for suppressing the noise photons, we have established the entanglement between the photons after the frequency conversion and another photon of the SPDC photon. And then more recently, the PPL waveguide is works for only the V-polarized photons. So when we want to use the polarizing photons for the carrier of the quantum information, the PPL waveguide cannot be used because the H-polarized photons cannot be frequency converted. So to overcome this problem, we use the Sagnac interferometer and install the PPL waveguide into the interferometer. We achieve the polarization insensitive QFC, in which the polarizing photon is input to this interferometer, and the H-polarized photon passes through the clockwise direction to this interferometer, and the pump light is prepared at the diagonal polarization. So the H-polarized pump light passes through this direction. So using the wave plate, the H-polarized photon is flipped to the V-polarization. Then the frequency conversion can occur at this crystal, and then the V-polarized converted photon is extracted from this line, and then the wave plate flips the V-polarized to the H-polarization. The H-polarized converted photon is obtained. On the other hand, for the V-polarized photon that passes through the counterclockwise direction at this interferometer, and the V-polarized pump light also passes through the counterclockwise direction. So the frequency conversion occurs at this crystal. Polarization is flipped at this wave plate, and the H-polarized photon is extracted from this direction, and then this wave plate again flipped to the V-polarization, and finally the V-polarized converted photon is obtained. And similar to the conventional Sagnac interferometer, the phase information between the clockwise direction and the counterclockwise direction is preserved. So the superposition between the H and the V polarization is preserved. And then the quantum state encoded into the polarization is preserved after the frequency conversion. And in this paper, we use the atomic Lubizim cloud, and then the entanglement between the 780 nanometer photons and the Lubizim atomic cloud is prepared using the Lubizim atomic systems. And we perform the QFC experiment using this PI QFC. And finally, we have demonstrated the entanglement preservation after the frequency conversion using this system. And such a system has been applied to many quantum communication systems using the quantum matter systems over long distance. The first demonstration using the deployed fiber is what was reported from the Zhang Wenpeng group in China. And in this group, the Lubijima cloud is used at the two end nodes, and then the photons emitted from the Lubijima atomic cloud is converted to the telecom wavelengths, and then at the middle point, the two photon interference is performed at the telecom photons after the transmission, and then they achieve the entanglement between the remote Lubijima atomic clouds separated at the Alice and Bob. And a similar experiment has been reported from the Weinfurter group, in which the PIQFC was applied to convert the polarizing photons to the telecom wavelengths, and they performed the two photon interference after the 10 kilometer transmit, 20 kilometer transmission, and they established an entanglement between the single atomic system of the Lubijima atoms. And for example, in the Hanson's group, they perform the frequency conversion of the photons emitted from the NV center, and then they convert the photons to the L-band telecom wavelengths, and they establish an entanglement among these two remote parties, which are connected at the deployed fibers beyond the laboratory. And the Luking's group reports the long distance communication as explained in the previous talk. And on the other hand, recently in the QKD, in the field of the QKD, the frequency multiplexing has been widely studied for achieve the high capacity or high speed or multi-user quantum key distribution systems. So in the quantum internet, beyond the QKD, the frequency multiplexing should be included in the quantum internet for the fast communication between the distant parties using the matter systems or quantum devices. So the QFC technology should be extended to the frequency multiplexed context. So for this, we recently performed the QFC system, which converts the fixed frequency photon to frequencies at the any frequency channels of the dense DWDM frequency channels at the telecom wavelengths. And then after the transmission for the Bell state measurement, we should pick up one of the photons passed through the coming from the in this using this protocol, the frequency multiplexing is used as the optical fiber, and for establish the Bell state measurement between the photons coming from any channels of the frequency multiplexed channels, like lambda 1 and lambda 2. So to achieve the Bell state measurement, the QFC system at the repeater nodes should have the ability to convert the photon from any frequency photons to fixed frequency photons. So, and in addition, the other frequencies photons, which are not converted to the different wavelengths, the photons passes through other quantum should passes through the other quantum networks. So we demonstrated this QFC systems from N to 1 using the cavity structure, which I explained later. Okay, I first explained the 1 to N channel selective quantum frequency conversion. As I explained, the photons at the frequency omega s can be converted to omega c using the omega p pump light. So when we use the different frequency pump light, the converted frequency can be chosen using the different frequency by switching the frequency of the pump light, like this figure. So if the photons emitted from the matter qubit is time multiplexed, this N1 to N QFC can be easily achieved using the switching of the pump light. So using this system, we can achieve the free connected multipartite network we can establish, like this figure. And for example, Alice has the rubidium atom, the Bob has a LV center, and the Carol and Dave has any kind of the matter qubit. And when we want to establish the entanglement between Alice and Bob, the frequency QFC converts the photon to the omega 1, and then the Bell state measurement is performed at this system, and then the entanglement between the Alice and Bob is established. And when we want to establish the entanglement between Alice and Carol, the frequency conversion should be performed to the omega 2. And in this case, this Bell state measurement guarantees the entanglement between the Alice and Carol. And using the similar systems, we can establish that any two of the n parties can be achieved using this system. And in this system, the Bell state order of the required number of the Bell state measurement is n squared. But using the Beijing theorem in the graph theory and with the use of the multiplexes and the demultiplexers, the number of all of the components can be scaled to order n. So we can scalably establish the free n-partite quantum networks, including the matter qubit with QFC technology. And this is the experimental setup. I'll explain briefly. The channel selected QFC is achieved at this conventional PPL waveguide, and we prepare the switchable pump light sources around the 1580 nanometers, and one of the pump light is selected using the this optical switching system, and using the N21 DW Demax multiplexers, pump I is selected after these selectors, and then the pump I is amplified using the EDFA, and then it is input to the PPL waveguide. And when the omega I is used for the pump frequency, the frequency converted, the corresponding frequency after the QFC is achieved. And then it is demultiplexed using the demultiplexers, and the photons comes from the desired frequency channels after the frequency conversion. And we can adaptively select any one of the pump light from the this pump light sources. Also, we can achieve the channel selective frequency conversion from the 780 nanometers to the telecom wavelengths. And important property of the switching system is the band efficiency and the bandwidth and the switching speed and the SNR of the QFC system. And we characterize the one by one in this experiment. First of all, the bandwidth of the QFC system is over the 2.5 terahertz, which corresponds to the 100 channels when we use the demultiplexing systems with a channel spacing of 780 gigahertz, also 25 gigahertz. So very large frequency multiplexing channels can be used with this switching system. And the switching speed is also very fast in this using this system. About the 1 microsecond switching speed is achieved. So this is enough for using the QFC system to convert the photons emitted from the matter systems, because conventional photons emitted from the atomic system or ionic system have the line widths of about megahertz or the kilohertz, which corresponds to the microsecond photons or millisecond photons. So this 1 micro switching speed is enough to select the frequency multiplexed photons emitted from the ion or atomic systems. So this can be easily installed to the quantum interconnect between the matter systems with the use of the frequency multiplexing technology of the photon transmission. And the property as a QFC device, this has a very large SNR with low noise properties in the quantum frequency conversion process. And this is the experimental result when we use the photon pairs with the cross correlation functions 18 before the frequency conversion, and then one of the photon is converted to the different wavelength, telecom wavelengths using this QFC device. And after that, we measure the cross correlation function after the frequency conversion. This is the result of the cross correlation functions by using the 7 different pump frequencies. And from this figure, the corresponding frequency channels at this demultiplexers, the very high cross correlation functions were observed. And on the other hand, from the other channels, the observed cross correlation functions are about 1, which means the no correlated photon is extracted from the undesired channels. So this means that only the noise photon is included, and the signal photon is mainly extracted from the only the desired channel. So this means the channel crosstalk, there is no channel crosstalk in this system. So very clean QFC system is established using this channel selective frequency conversion. Okay, next, I explained the frequency conversion, channel selective frequency conversion from N to 1. This, in contrast, different from the N to 1 to N channel selective frequency conversion. N to 1 frequency conversion is very difficult because a conventional QFC has a very wide phase matching condition. So selection of the one of the photon from the multiplexed channel is very difficult in, for example, using the PPN waveguide or KTP waveguide and so on. So to extract the one of the frequency from the frequency multiplexed channels, we use the cavity structure in the QFC system like this one. So the energy diagram of this QSC system is described like this. The frequency of photon is frequency multiplexed like around the omega s, like this figure. And the frequency of the pump light is only omega p. In this case, when the converted frequency at omega c is resonant to this cavity resonant frequency, the frequency conversion occurs, and then the frequency conversion converted photon is obtained. But on the other hand, if the omega c is not resonant to this cavity after the frequency conversion, the DFG process is suppressed because of the non-resonant condition through the frequency conversion. So, for example, in this case, lambda 1 and lambda n cannot be frequency converted to the frequencies around omega c. This is not coupled to the cavity, so this passes through the material without the frequency conversion. So by selecting the pump light at omega p, we can select one of the frequency from the frequency multiplexed input to this conversion system. And we can achieve the N21 frequency QFC converters. Such a system has an analogy of the optical tweezers used for the trapping the atomic systems in the frequency domain. So we call this device as optical frequency tweezers, which can precisely select one of the sites deployed at the frequency domain, and we can precisely pick up this photon and move to the different site of the frequency degree of the freedom. So this is like the optical tweezers, which can tweeze single atoms and at the spatial modes to the different spatial modes. So very similar to the optical tweezers. And this is the energy conservation law of the QFC system. So when the frequency spacing of the frequency multiplexing is delta com, in this case, when we convert the omega s plus delta omega com, the pump light at the frequency of the frequency of omega p minus delta com should be used for the frequency conversion. And this is the experimental result for the proof of principle experiment for the optical frequency tweezers using some frequency generation using the laser light. We performed the experiment from the frequency multiplexed input at around the 1540 nanometer signal light with a channel spacing of 1 gigahertz. And when we use the pump light at around the 1580 nanometers, and this tooth is used for the QFC experiment, only this tooth of the signal is frequency converted to 780 nanometer photons light. And when we use the pump frequency at the detuning of 1 gigahertz, like this figure, this tooth with the frequency difference of this figure is 1 gigahertz, but the converted frequency is exactly same as the 780 nanometers. And using the pump light with the omega p plus 2 gigahertz, like this figure, the second neighbor's tooth is frequency converted to the same frequency. And if we, more interestingly, the cavity structure has a resonant frequency with the channel spacing of the FSR. So if we use the omega p plus 33 gigahertz detuned frequency as the pump rate, which corresponds to the this corresponds to the 10 FSR of this system. And in this case, the frequency of the to be converted is the same, but the converted frequency is different with the spacing of 33 gigahertz. So when we use the omega p minus 33 gigahertz, like this figure, the same tooth is frequency converted to the this frequency mode with the channel spacing of 10 FSR detuned frequency, like this figure. This is very complicated, so I explained. This is the frequency cone of the input to this frequency conversion system, and the channel spacing is delta cone. And the cavity structure is discretized with the channel spacing with corresponding to the FSR. So the image of the relationship between the channel spacing of the input and the cavity structure is like this. So when we use the pump frequency at the omega p, only this tooth is frequency converted because the converted frequency is resonant to this other cavity. But these three tooths never converted because they are not resonant to the cavity. So if we want to convert this signal mode to this resonant frequencies, the omega p plus delta FSR can be used for this frequency conversion system. And in this case, only this tooth is frequency converted to this frequency, but other three tooths never frequency converted. And if we want to convert this mode to this frequency, the pump frequency at omega p plus 2 delta com is used for the frequency conversion. And in this case, these three modes never frequency converted. So we can choose the one of the input frequency mode, and simultaneously we can select the frequency converted the frequency after the QFC with discretized at the channel spacing of omega delta FSR is selected. So this is we can understand these systems like this meshed figure, and this is omega S vs omega C, and using the pump light. For example, this site can frequency converted to any different sites using the frequency conversion. So using this cavity QST system with a cavity, we can selectively move the any frequency to any frequency around determined by the cavity and the input frequency, discretized frequencies. So for that reason, this can be understood as a frequency tweezers in the frequency domain. So we call this frequency tweezers. Okay. Do you have any questions? Okay. Oh, yeah.
General efficiency somehow limited or
efficiency? Using the cavity? The different from the conventional QC without the cavity, the maximum conversion efficiency is limited by the loss inside the cavity and relative to the mirror coupling loss of the cavity system. So this can be formalized, explained at the previous lecture. So there is a loss inside the cavity, and the frequency conversion is understood as a coupling constant, strength of the coupling constant between the cavity and the free mode. So the maximum conversion efficiency is determined by the ratio of the internal loss and the extract. And in this demonstration, the maximum conversion efficiency is limited to about 10 or 20%. That is because the cavity mode is constructed around the 780 nanometers. That has a traveling loss inside the PPN waveguide. So to obtain the higher conversion efficiency in this system, we perhaps the different material or the is better, or yeah. But as I explained in the previous slide, for the quantum internet applications, the loss of the 10% or several percent is enough compared to the system without the frequency conversion system, because the telecom band is very efficient through the over the long distance communication. Okay. Okay, from here, I explained another application of the frequency conversion system. That is the frequency domain beam splitter. As I explained, this frequency conversion system can be understood as a conversion system between the two different frequency modes of the higher AH and AL. So, and the input-output relation is described by this transformation matrix with the transmittance of cosine and the reflectance of the sine. So this is similar to the conventional beam splitters at the spatial domain. So when the omega h is input to this device, the omega L photon is obtained with the efficiency of sine theta. But on the other hand, if we input the lower energy photon to this device, higher energy photon is obtained with the reflectance of sine squared. So when we input the 2 photons from the both ports to this device, what happens? When the conversion efficiency is set to the 50%, that is can be understood as a half beam splitter at the different frequency modes. In this case, the Horn-Mandel interference should be observed between the different frequency modes. The Horn-Mandel experiment interference is two photon interference between the indistinguishable photons. So the indistinguishable photon is input to the half beam splitters. The 2 photons are extracted from the same output ports, and 1 photon from the port A and 1 photon from the port B never obtained due to the destructive interference between the 2 different modes, different events. So in conventional setup, when we add the optical delay between the 2 different input modes, the coincidence between the different output modes is described by this curve. As the delay is at the 0 delay, the coincidence disappears due to the interference parametric effect. But on the other hand, there is a very large optical delay. The 2 photons can be distinguishable. So the coincidence obtained. So in this case, we use the QFC device with a conversion efficiency of 50%, and the higher energy photon and the lower energy photon is input to this device. In this case, using the pump rate at omega p, the omega h is distributed to this blue port and the orange port, and the omega L is distributed to blue ports and orange ports. And due to the destructive interference between the different wavelength photons, these photons can interfere by the beam splitter interaction among the different wavelengths. This is the experimental setup. This is the beam splitter interaction of the QFC device with a 50% transmittance and a 50% conversion efficiency. And for the 2 different input photons, we prepare the 780 nanometer photons using the parametric down conversion using the BBO crystal. And then one of the photon is detected and heralding the 780 nanometer single photon. And on the other hand, the other 1522 nanometer photon is prepared by using the laser light with a mean photon number of 1. And the conceptual figure is this. A single photon is input to this QFC device, and the lower energy weak coherent light is input to this device. And with optical delay, delta t, the Horn-Mandel interference parametric effect is observed like this. And the visibility of the Horn-Mandel interference is about 70%, which exceeds the classical limit of 50%. So the QFC device as a beam splitter between the different color photons is what successfully demonstrated in by this experiment. So in the conventional textbook, the photons, only the indistinguishable photon can interfere between the beam splitter interaction, and the distinguishable photons never interaction. But using but the input of the two photons looks distinguishable at the frequency mode. But using the QFC device, this mixes the different frequencies, omega L and omega H. So this does not violate the constraint of the quantum mechanics and matches the theory of the written in the conventional textbook. Do you understand this phenomenon? Okay. So using the cascaded use of the frequency domain beam splitters, we can implement the frequency domain linear optical interaction similar to the conventional linear optical interaction using the spatially mode. And different from the spatially modes, these different frequency photons can be implemented in the single mode spatial modes. So very compact optical setup or the very massive mode linear optical computation can be in principle possible using the frequency mode, because we can use the frequency COM or the very massive mode frequency multiplex of photons in the current technologies. So this is suitable for the implementation of the large photonic quantum information circuit. Okay, so I explained the application of the Kaizu nonlinearity as a quantum frequency conversion in the previous slides. And from here, we explained the photon pair generation using the Kaizu nonlinearity. In this case, the pump light at the highest frequency is input to this Kaizu nonlinear material, and then the lower two photons are simultaneously prepared. That is known as the photon pair generation process, SPDC process, spontaneous parametric down conversion process. And different from the effective Hamiltonian used in the QFC interaction, the Hamiltonian is described by this, the creation operator of the L1 and L2 modes, and the element conjugate is used for the effective Hamiltonian of the SPDC process. And that is explained in the previous lecture. The SPDC photon process is occurs when the strong pump light is input to this nonlinear optical medium. The signal photon and the ideal photons are generated, and at the condition of the produce of the SPDC process is the conservation of the energy. The two conditions must be satisfied: the energy conservation, the phase matching conditions like this. So the joint spectral function of the SPDC process is usually described by this. The two photon joint spectral function is described by the function of the F determined by the center frequency omega p and the spectral width of the frequency. And the creation operators omega s and omega I is simultaneously appeared in this photon pair state of the photon pairs. And the omega s versus omega I is described by this figure. This width reflect the bandwidth of the pump frequency, pump light, and this direction means the phase matching condition reflects the with also the phase matching condition. In the conventional PPL waveguide, this direction, the length of this direction, the phase matching acceptance bandwidth is very large. And this direction is determined by the pump price. So that means when the CW pump laser is used, this is very narrow. But when we use the pulsed light, the delta omega p is large, so the bandwidth becomes wide. So in the conventional process, the frequency filtering should separate the frequency correlation between the signal photon and other ideal photons. So after the frequency filtering between the so install that the omega s and omega I generates the uncorrelated frequency uncorrelated photon pairs at omega at signal and the ideal modes. So using these photon pairs, we can establish the linear optical quantum computation, such as the entanglement swapping or the nonlinear optical gate, using the linear optics standard post-selection process. And the effective Hamiltonian after the frequency filtering is described like this. And the quantum state of the SPD photon pairs can be described like this figure, like this equation. And the gamma is the excitation probability is very small compared to the one. The single photon pair is extracted at the signal and the other modes. And this is an example of the frequency multiplexing of the QKD protocol using the entanglement photon pairs produced by the spontaneous parametric Dirac conversion. This is the Sagnac interferometer to produce the polarization entangled photon pairs using the SPD process. And similar to the polarization insensitive QFC, the clockwise direction produces V polarized photon pairs, and the anti-clockwise direction produces the H polarized photon pairs. And the process is superposed. HH and plus HH plus VV photon pairs is this generated. And the phase matching condition is very large in the PPL waveguide. So we can extract the many photon pairs at different frequency pairs at omega s and signal and ideal modes. So using the conventional demultiplexers, the multipartite quantum network is established. So this is one of the approaches for achieving the frequency multiplexed quantum QKD network. And another approach to produce the frequency multiplexed photon pairs is the use of the cavity and the non-linearity inside the cavity. So, for example, these microring resonators produce the photons only for the around the resonant frequency of the cavity. So due to this cavity structures, the discretized frequency pairs at signal and ideal modes are generated after at the nonlinear interaction. So in this case, the photon pairs are described by this. That is the discretized frequency mode is described by the label M and the omega SM, and the tensor product of the omega SM and the omega IM is generated by this process. And this different pairs have the fixed phase information. So this is not just the frequency multiplexed photon pairs, but also the frequency common, similar to the conventional optical frequency common for realized by the laser light. So this state is called as a biphoton frequency cone or quantum frequency cone in present day. And we consider in our laboratory we consider the generation of the quantum frequency cone using the conventional PPN waveguide. And from the previous studies, the simple approach to produce the frequency discretized photon pair generation is achieved by this setup. This confines this confines both signal and ideal modes, and the Kaiser medium inside the cavity produces the SPD photon pairs. And but due to the omega dependency of the FSR of the PPN waveguide, the photon pairs never produced within the very large frequency regions in this setup, because for the photon pair generation, not only the energy conservation but also the simultaneously cavity resonant conditions of the signal and ideal photons should be satisfied. But due to the this omega dependencies, even if this pair satisfies the cavity resonant condition and the energy conservation simultaneously, other frequency pairs may not satisfy the cavity resonant condition and the energy conservation law simultaneously. As a result, at this frequency pairs, the photon pair is generated. But in contrast, this frequency SPDC photon never produced. So the clustering effect of the photon pair generation is observed using this cavity SPDC process. So the bandwidth of the photon pair generation is very limited by this system. So massive mode of quantum frequency cone never obtained. That means a large number of the frequency multiplexings cannot be achieved by this setup. So to overcome this problem, we use the singly resonant SPDC process using the cavity only for the signal mode. This cavity confines only the signal photons, but does not confine the ideal photon. In this case, what happened? The signal is confined in the cavity, so the produced frequency has a resonant structure reflecting this cavity structure. And due to the energy conservation, in spite of no resonant structure in the ideal mode, the ideal shows the frequency discretized spectrum as if it is confined into the cavity. So using this singly resonant SPDC process, we obtain the frequency cone. And this condition this cone structure must satisfy the energy conservation, but there is no need to satisfy the severe condition for the frequency cavity resonant condition for the both signal and ideal modes. So wideband frequency discretized photon pair is obtained using the SPDC process without the clustering effect. Using the system, we achieved over 1,000 modes frequency multiplexing with a fixed phase relationship. So the biphoton frequency comb we obtain. This is an experimental implementation of the cavity resonant single cavity, the PPL waveguide with a single resonant cavity for the signal mode. The pump light frequencies wavelength is 780 nanometers, and from the ISPDC process, the photon pairs around the telecom photon is generated. And the reflectance at the both end faces is described by this figure. And the pump light is, for the pump light, the anti-reflective coating is achieved by this dielectric coating. And for the ideal photons, the anti-reflective coating is achieved around the 1500 nanometers to the 1550 nanometers. But on the other hand, for the signal light around the 1560 nanometers to the 1560 nanometer to the 1600 nanometer is high reflective coating. So the cavity structure is achieved for around the wavelengths, signal wavelengths. So to observe the property of the biphoton quantum frequency comb, we use the CW pump laser to produce the photon pairs, and then we separate the signal and the ideal photons and perform the coincidence measurement between the photons. And when the bandwidth of the filter is very large, that means it that contains the extract the 33 frequency modes, a superposition of the different frequency modes, like this figure, like this equation. In this case, the beating effect of the different frequency modes obtained, so the oscillation of the coincidence is observed with the periodic period reflecting the FSR of the cavity. On the other hand, when the very narrow frequency filter is used, which contains only the one frequency mode, which in this case, there is no superposition between the different frequency modes. In this case, only the exponential decay determined by the Lorentzian filtering by the cavity is observed to the coincidence measurement between the signal and the ideal photons. So this result showed this process produces the quantum frequency comb using this single resonant PPL waveguide. And to observe the no clustering effect, we observe the single count within the region of the telecom wavelengths, very wide range. So the photon pair generation rate have the same order around in this region. So this means different from the previous experiment that confines both of the both signal and ideal photons. No suppression region is observed in this measurement. So very much quantum frequency comb is generated by this. And to obtain the very massive frequency multiplexed polarization entangled photon pairs, we use the Sagnac interferometer like this. Inside the Sagnac interferometer, the PPL waveguide with the cavity, single resonant cavity is installed at this point. And diagonal polarized pump light is input to this interferometer, and the HH and the superposition of the HH and the VV is produced at this interferometer. And then the frequency discretized polarization entangled photon pair is generated by this interferometric photon pair generator. And from this result, the fidelity larger than the 70% and around the 80%. That is much higher than the threshold of the entanglement existence is observed around the 15, 16 nanometer to the 1600 nanometer region. So similar to the previous experiment I explained here, the massive mode polarization entanglement is observed by this setup. And after that, we use the PPLN waveguide with a cavity with a PPLN chip length is a 5.6 millimeter length that have the FSR corresponding to the 12.5 gigahertz compatible with the DWDM system. And using this system, we distribute the frequency discretized polarization entanglement photon pairs to the Alice and Bob using the demultiplexers with 16 different frequency channels. And we observe the fidelity over 90% in all of the different frequency modes. So using this system, we have established the frequency multiplexed entanglement using the cavity resonant PPLN waveguide. This is the one of the applications of the quantum frequency entanglement, quantum frequency cone with polarization entanglement. But in recent studies, the quantum frequency cone we found that the quantum frequency cone can be used as a new photonic source for the quantum information processing based on the frequency domain of the freedom. In the conventional photonic qubit, it's implemented using the path information, polarization information, or time being or frequency being. But different from the polarization, the time being and the frequency being can be extended to the qubit system. So there is a possibility to realize the new quantum information processing beyond the qubit system. And there are a lot of experiments and the theoretical approach to implement the time being and the frequency being a qubit. But different from the time being or frequency being approach, we construct the qubit using the superposition of the frequency cone with a different offset like this figure. And this frequency cone is encoded to ket0. And this frequency cone with a different offset is encoded to ket1. And we use the superposition of the frequency cone as a qubit system. And different from the time being or frequency being qubit, the Fourier transform of the frequency cone is also has a COM structure in the time domain. So the COM structure is preserved in both frequency and the time domain. So the error tolerance is balanced among the frequency and the time domain in this construction. So this is similar to the GKP qubit encoded into the phase space using the X and P. The GKP is this qubit system encoded into the X and P with a discretized structure, the GKP. In the GKP system, there is a discretized photon distribution among the in the phase space, like this figure. And similar to this structure, that our frequency based qubit system has a discretized spectrum in the time and frequency domain. So this structure is similar to the original GKP system. So this is called as a TF time frequency GKP qubit. And using the several different offset beyond the qubit system, this can be easily expanded to the qubit system over larger than the Ket0, Ket1, and Ket2, Ket3. So this is a new candidate to realize the linear optical fault-tolerant linear optical quantum computation. And one of the, so what we must consider is how do we implement the generation of the qubit, initialization, manipulation, and measurement. And in this paper, we propose a concrete way to realize such a preparation and manipulation and detection system for the TF-GKP. The preparation is similar, is realized by using the cavity-enhanced SPDC process described in the previous slide. So using this system, we can prepare the qubit encoded into the frequency COM. So the TF-GKP state can be prepared by this system. And time resolving detector implements the Pauli-X measurement on the qubit system encoded in the TF-GKP. And the frequency resolving detectors implements the Z-state measurement on this qubit, because the spectrum of the Ket0 and Ket1 is different, so the frequency filtering implements the Z-state measurement. And the time resolving detector performs the measurement with a superposition of the frequency spectrum. So the superposition of the 0 and 1 is implemented by using the time resolving detector. And what is the beam splitter for the frequency COM? That is implemented by the optical interleaver used in the conventional optical devices. So when the superposition of the two frequency COM is input to the optical interleaver as a beam splitter for the TF-GKP, the Ket0 and Ket1 is separated by this beam splitter. So using this, the beam splitter, it can be implemented. And using these basic elements, we can implement the many different quantum devices like this. The measurement in the superposition of the X and Y basis is implemented by this setup. This measurement with capital T is a time resolved detector. Under Bell state generation, this Bell state measurement, Bell state generation of the TFG KP is implemented by this optical circuit using the conventional beam splitter and the optical interleavers. And the fusion gate is implemented by this setup with the two ancillary qubits encoded into the ket 0 plus 1 that is described by the ket 0 in the time domain. So using these three devices, we can construct the measurement-based linear optical quantum computation using the TFG-KP that is similar to the measurement-based linear computation using the polarization degree of the freedom written in this paper. So yeah, this is sufficient for fault-tolerant measurement-based computation. And the final question is the error analysis for when we use the optical device, realistic practically optical devices for the time resolving finite with a finite resolution and the including the typical errors in the optical devices. How is the errors on the qubit? So there are two types of errors in the time frequency domain. Time frequency GKP qubit. One is the both time and frequency basis, the broadening of the spectrum broadening of the spectrum generates the errors on the qubit because the discrimination becomes the degree of the discrimination among the different frequency mode or the time mode becomes small. So this is one of the errors on the qubit. And another error is the fluctuation of the frequency of the time domain of fluctuation of the center frequency or time peak generates the errors on the discrimination of the ket 0 and ket 1. So we must care the two types of the errors on the TFG-KP qubit system. And the fluctuation or the spectral broadening comes from the finite temporal resolution of the detectors. And the state of the experiment using the SSPD system have only the 4.3 picosecond time, very small timing resolution, a very large time resolution. So the short fluctuation is induced by this detection system. And common spacing of the optical interleaver and the frequency comb is achieved as a 12.5 gigahertz using the conventional optics, commercial optical interleaver we can obtain by the for example, the optoplex. And we can also generate the frequency comb with a channel spacing of 12.5 gigahertz, which we have experimentally demonstrated in the previous slide. And the finesse of the frequency comb means how the spectrum is sharp and how the different spectrum is clearly separated as a clear qubit. The finesse is about we have achieved in the experiment is about 60. So using these parameters and for estimating the errors onto the TF-GKP qubit, the error probabilities, the estimated error probabilities is less than 1% is achieved. So 1% is a conventional threshold of the fault required threshold for the linear optical quantum computation. So using the current technologies and the optical devices, we could achieve the fault tolerant linear optical quantum computation system based on the TF-GKP qubit system. Okay, I summarized my talk. For the quantum internet, we developed the quantum frequency conversion based on the Kai2 nonlinearity. And for the recent development of the frequency multiplexing of the QKD or the frequency multiplex quantum internet, we demonstrated the channel selective quantum frequency conversion from the fixed frequency to the any frequency mode of the frequency multiplex system. And as a reverse process, we using the resonant QFC system, we can achieve the quantum frequency tweezers, which can extract only the one of the frequency modes from the frequency multiplex input to the desired frequency after the frequency conversion. And then any frequency photons can be interfered at the Bell state measurement system. So any different channels can be entangled after the Bell state measurement with the channel selective QFC. And in addition, the singly resonant Kai2 nonlinearity can be applied to generate the frequency multiplexed SPDC photon pairs with a fixed phase relationship among the different frequency modes. And this can be applied to the new kind of the qubit implementation using the time frequency GKP qubit, which is encoded into the two different frequency comb for the Ket0 and Ket1. And using this and the currently developed optical devices, fault tolerant linear optical computation is expected using this encoding. Thank you.